This is a lecture on the chain rule in multiple variables. And we start by recalling what we know about the chain rule from Calculus 1 in one variable. So if we have a composite function where y is a function of x, and x itself is a function of t, then we write the resulting function of t, y, as f of g of t. And we know from Calculus 1 that the derivative of such a function is given by the chain rule, where dy dt is f prime of g of t times the derivative of the inside g prime of t, which can be written df dx times dx dt. Now, a common way of interpreting this chain rule in one dimension is with the idea of gears. And I'm sorry that I don't have any pictures of gears here on the page. They wouldn't be very pretty if I drew them. But the idea is to imagine that t, as t is moving, it is turning a gear called x. And that's given by this function right here, dx dt. Similarly, x is connected by another gear to this quantity f. So x is like one gear, it's turning at a rate dx dt. F is connected to x, and it's another gear, and as t evolves, it turns the gear x, which turns the gear f. And so the total rate of change of f is the product of the rate of change of x times the rate with which x turns f. So this is just some image that you can have in your mind. You might pause the video and think about that for a few minutes, that t is a driver for x, and x itself is a driver for f, and so the proper thing to do to find the rate of change of f is to multiply the two numbers together. So just as a brief review, here we have an example. Y equals x squared, x itself equals sine t. That means the composite function is y equals sine of t quantity squared. The derivative can be written dy dx dx dt, which is written 2x, where x equals sine t, times the derivative of sine with respect to t gives us cosine. And of course, we can then plug in that x equals sine of t to get 2 sine of t cosine of t. So that's what we have there for our chain rule. So just a simple warm-up example to remind us of our 1D chain rule. Okay, so now the idea is to go to higher dimensions. So suppose we have some function of two variables. Suppose we have a variable z, which depends on the variables x and y via the function f. But x and y themselves are both functions of t. We could call those functions g of t and h of t. So now, as t changes, x and y both change under these expressions here. And as x and y change, they cause z to change. And so the question is then, how does z change with respect to t? And using the same analogy, we won't prove this using the limit definition of a derivative, which is what we should do. But by sort of much coarser intuitive reasoning, we can imagine that z here is some quantity that changes. Change is driven by changes in x and y. However, x and y are both changed by t. So as t changes, t itself changes, it causes x to change at a given rate, and it causes y to change at a given rate. And so both x and y then cause z to change. And so we might expect some kind of sum where x is contributing to the rate of change of z and y is contributing to the rate of change of z, but each one of those independently also is dependent on the rate of change of x and y with respect to t. And so this is merely stated, and it would be nicer if we proved it, but it's merely stated. The chain rule in this first case, where x and y both depend on only one underlying variable called t, is precisely an expression of this intuitive reasoning that we used on the previous page. So dz dt is given by the rate of change of z with respect to x times the rate at which x itself is changing with respect to t. So here's the contribution to the rate of change of z from x changing, plus this additional term, the rate of change of z with respect to y times the rate of change of y with respect to t. So the contribution to z from y changing. Both of these terms are ultimately driven by t, and there's only one underlying variable t, and so this variable, this derivative dx dt, dy dt, and ultimately dz dt, those are all full derivatives because there's only one real underlying independent variable, which is t. X and y could be thought of as intermediate variables, which are only changing because t is changing. So we use the full derivative notation for dz dt, dx dt, and dy dt. Again, we can use this analogy of like gears, although it kind of breaks down because you have two gears connected to the z gear. But if you'll bear with me for a minute, suppose y is one gear which is turning at some rate given by dy dt, and x is some other gear which is evolving, it's turning at some other rate dx dt. Those are both connected to z, and each one of them are driving z at a certain velocity given by dz dx and dz dy. So that may or may not help, but it's a commonly used analogy. Now, let's just do an example to see the actual calculation is not very different from what you did in Cal 1. So it's not all that difficult to plug your way through. It just can become sort of cumbersome with a lot of algebra. But here's an example. So we have a function z equals f of x and y equals 2 plus x squared plus y squared. And this should look kind of familiar from a couple of sections ago. This is in fact one of our quadric surfaces. And if we think about it, look at it for a while, z equals 2 plus x squared plus y squared, that is a paraboloid. It is technically an elliptic paraboloid, but we have called it simply a bowl. It is something that opens upward because of the positive x squared and positive y squared. And it looks something like this sketch. Now, suppose that x of t is given by the expression 2t, and y of t depends on t like t squared plus 3. How does z change as t changes? So we can think of these two equations here for x and y as representing a parametric curve in the plane, the xy plane. And so as x and y evolve, they trace out a curve like this in the xy plane. So x starts negative and becomes positive. Linearly, it grows linearly with time. Whereas y starts large for large negative t, and then as t gets close to 0, it reaches a minimum value of 3, and then it goes back out to large values again. So this actually traces a parabola in the xy plane. If this is the trajectory of x and y, then we simply raise this curve up onto the paraboloid here to get that line on the paraboloid, which is the actual trajectory, the actual change in the value of z as t changes. So as t changes, it traces out this sketch, this line on the paraboloid. And the question is now, what is the rate of change of z as this curve is traced out on the paraboloid? So that's a lot of talking, but the calculation is quite simple. We simply say that dz dt is df dx, dx dt, plus df dy, dy dt. Df dx in this case was 2x, df dy is going to be 2y, dx dt is 2, and dy dt is 2t. And so we get those things, we plug them in, 2x times 2, 2y, 2t, and we get this expression here. We can finally then go back and replace all our x's with the appropriate expression in t, 2t and t squared plus 3, and we get a final result from our chain rule that only depends on t, as expected. We have a full derivative here, and so the result of the chain rule only has one variable. Okay, so a simple example. Now let's make it a little bit more challenging. Again, let's consider functions of two variables. So we have here a function, z equals f of x and y. But now suppose that x and y both depend on two independent variables, two underlying variables. We'll call them s and t. So x depends on s and t, y depends on s and t. So now, if we want to take derivatives with respect to the underlying variables, they will be partial derivatives because there are now two of them. so we can differentiate either with respect to s or with respect to t. Remembering from the lecture on partial derivatives that if we're taking a derivative with respect to s, then t is treated as a constant, we would expect to see exactly the same kind of formula, only with maybe partial derivatives instead of full derivatives. And that's exactly what we see with the chain rule. Again, this is just stated without proof. But if we take the partial derivative of z with respect to s, when we're doing that, we hold t constant. And if t is like a constant, then we get the same kind of formula in the remaining variable s that we did above. So we get d partial z partial x, except now all of the derivatives with respect to s are partial derivatives because there is a second independent underlying variable t. So the partial derivative of z with respect to s is given by this formula here, and the partial derivative of z with respect to t is given by a very similar formula, but with all the t's replaced by s's. So let's do another example. Suppose we have z equals e to the x cosine y, a function of two variables, and x and y both depend on both t and s. So function of t and s, function of t and s. What is the partial derivative of this function with respect to s? Well, we take the partial derivative with respect to x of z, right here, times the partial derivative of with respect to s of x. So this is dz, this is dz dx, partial x partial s, plus partial z partial y times partial y partial s. And so it's just a matter of calculating partial derivatives of these things on the inside, which we go right back to the previous lecture of holding things constant. So when I take dz partial z partial x, I treat y as a constant, e to the x cosine y. When I take partial z partial y, x is a constant, I get minus e to the x sine y. And then these other derivatives with respect to s are just constants, 2 and 1. And so now it's just a game of simplification. I can replace my x with its actual definition, t plus 2s. I can replace my y's with t squared plus s. And then at the end of the day, there's a common factor of e to the t plus 2s. So I can write down a final result of taking a partial derivative with respect to s. Again, we see that this depends on two variables, t and s, and so it is properly a partial derivative rather than a full derivative. The story is very similar. To take the partial derivative of z with respect to t, I've plugged in exactly the same things here, except I have changed my partial derivatives to t instead of s at the end, and I get very similar things. I then replace again my x's with the original definition of x, and my y's with the original definition of y. And I plug that in to get something that only depends on t and s. So it can become a little bit algebraically cumbersome. This is a good opportunity to practice your algebra when you are doing these problems. But conceptually, it's very much just partial derivatives, which, as we saw previously, is very much just single derivatives holding the other variables constant. So this process can be generalized to be as complicated as we want. We can have as many intermediate variables, x, y, z, w. In general, when we have lots of them, we just number them x1, x2, x3. And all of those x's can in principle depend on as many underlying variables as you want. If there are many of them, we number them again, t1, t2, t3. And so then if we want to take a partial derivative with respect to one of those underlying variables, say t1, here I think I've notated it just ti, it's the same in all cases. For every different value of I, the partial derivative of z with respect to that variable ti is just a sum of all the different terms, derivatives of the intermediate variables times the partial derivative of that intermediate variable with respect to ti. So dz dx1, dx1 dti, plus dz x2, dx2 dti, and so on all the way down the line. If there are n intermediate variables, there will be n terms in that expansion. So here's an example. Suppose w. We now have w as a function of three variables, x, y, and z. And x, y, and z are all functions of the three variables, or the two underlying variables, t and s. So we can take partial of w with respect to s. That will be the partial of w with respect to x, which is 2x, times the partial of x with respect to s, which will be 4s, and we have this term here. Then we will take the partial of w with respect to y from here. That gives us z plus times the partial of y with respect to s, which is -4, plus the partial of w with respect to z, again, from this term, that gives us just y, times the partial of z with respect to s, which is -3s squared. So we get all these terms. We replace the x's, the y's, and the z's with their proper formulas from this set of equations here, and we get a bunch of terms, and then we do algebra, we simplify those terms to get a nice, well, relatively compact expression for dw ds. And so on. I'm not going to repeat this calculation for all the different partial derivatives, but you could do that as well to practice these problems. Okay, last topic in this lecture is the topic of higher derivatives. So we've talked about calculating first derivatives using the chain rule. And let's go back for simplicity to the simplest possible chain rule example, where we just have two variables. Z depends on x and y, for instance, and the two intermediate variables depend on one underlying variable, in this instance just t. So we've seen how to take first derivatives. How do we take second derivatives? What is d squared z dt squared? Again here, because there's one underlying variable, these are full derivatives. Now, here's our result from earlier in the video. dz dt is partial f partial x times dx dt plus partial f partial y times dy dt. Again, that's the contribution from both x and y to the change in z, each of which is multiplied by the underlying rate of change of x or y. So the second derivative with respect to t is going to be d by dt of the first derivative, right? It's just the time derivative, the derivative with respect to t of the thing that we just calculated. But how do we do that? Well, we're going to have the time derivative using, this is all going to be product rule. We have the time derivative of partial f partial x times dx dt plus partial f partial x times the second derivative of x with respect to t. That's from this term. And then from this second term here, we have the time derivative of partial f partial y times dy dt plus partial f partial y times the second derivative of y with respect to t. Now here's where it gets messy. It's very unfortunate. Both fx and fy depend on x and y. These are partial derivatives, and so they are just functions. They are functions of x and y, however, and x and y both depend on t. So in order to calculate the time derivative of these two objects, we're going to have to use the chain rule again. So this is just one piece that we're now calculating. The derivative with respect to t of fx is the x derivative of fx times the t derivative of x plus the y derivative of fx times the y derivative of, or times the t derivative of y. The time derivative of df dy is the y derivative of df dx times dx dt plus, I made a mistake, the x derivative of df dy plus the y derivative of df dy times dy dt. So then we have to take these expressions, these are just the chain rule derivatives with respect to t of df dx and df dy. We have to plug those back into our original formula here and here, and it gets long. So in the end, we have all these terms. Here's our t derivative of df dx times dx dt plus df dx d squared x dt squared, and so on. We get all these terms, and it's a lot of terms. So there's no shortcut. There's no simpler way to do this. You just have to be master of the chain rule and the product rule and use them over and over and over again. The key thing I can say is to use this notation d by dt whenever you're not sure what to do. So we have a a formula for dz dt, and we can write that down, and you say, well, what's the second derivative? And you might be tempted to just put second derivatives up here somewhere, and that would be wrong. The second derivative is nothing more than the derivative of the first derivative, and so if you write the derivative of the first derivative, and then you use your product rules, you will see where you then have to use another instance of the chain rule. So it's fine to write this out in as many steps as you need to make sure that it is clear in your head exactly what you need to do. You just need to do it a few times and practice, and it will become natural. So we conclude, I think, with an example. Relatively simple function, f of x and y is x squared y squared, where x equals 2t and y equals t cubed plus 3. These are the same x and y as a previous example, but a different f. So the first derivative of f with respect to t is the derivative of f with respect to x, that's 2xy squared, times the derivative of x with respect to t, plus the derivative of f with respect to y, 2x squared y, times the derivative of y with respect to t, 3t squared. The second derivative is the first derivative of the first term plus the derivative of the first term plus the derivative of the second term. Okay, so I just use this d by dt notation. It lays everything out for me. I haven't had any chance to get confused yet, and I say, okay, well, here I have a product of two terms, and I'm going to have to use the chain rule again. So I have the derivative with respect to x gives me 4y squared times dx dt right here. Then I have the derivative with respect to y, which is 8xy times dy dt. And so these two terms go with this first term here. Now here in this second term, I have three things. It's a product of three things, x squared, y, and t squared. So my product rule is going to give me three terms. The first term is the derivative of this term with respect to x, which is here, times dx dt, plus the derivative of this term with respect to y, which is here, times, using the chain rule, dy dt. And then I also have this t squared in there, and so there I can just take the derivative with respect to t itself. And there's no application of the chain rule because t is the variable. I'm not taking the derivative with some other variable and then having to do the derivative with respect to t. So I get these three terms here from this second term up here. And I just can add them all together. In principle, I would then have to replace all my x's with 2t and my y's with t cubed plus 3, and I would get a whole bunch of terms and simplify, but that is not really the point of this lecture. That's just algebra. So we'll stop there.